Hi, my name's Jess. Thank you for taking the time today to review my course project, Machine Learning Foundations for Product Managers, Duke University through Coursera. Our goal here is to build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam engines, and heat recovery steam generators to generate power. There is active competition to reach higher efficiencies in this industry, and predictability is an important asset to gaining a competitive edge. We have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant, which we will use in our model. I chose to use option 1 to complete the task in Excel. I built a multiple regression model to predict power output, PE. The columns or features in the data consist of hourly average ambient variables, temperature, ambient pressure, relative humidity, exhaust vacuum, and of course the net hourly electrical energy output, which is the target we're trying to predict. In this presentation, I'll walk you through my modeling approach, the comparisons I made, and the final evaluation that led to my conclusion. Since the outcome variable, PE, is continuous, this is a regression task. As a starting point, I tested multiple linear regression as the baseline model. All variables were statistically significant, but AP had the largest p-value highlighted in the presentation, making it the least influential predictor. I tested removing AP to provide a different combination of features, and the simpler model still performed with very good accuracy. Polynomial regression was also considered, but feature reduction was chosen for greater clarity and simplicity. Data was carefully segregated into sets before beginning work to avoid data leakage. Both models were trained on the training set, about 64% of the data, and validated on a separate validation set, about 20% of the data. The baseline model included all 4 predictors, while the reduced model excluded AP. This enabled a comparison of model performance to determine whether all predictors were necessary. The best performing model was then tested on the final test set, 16%, to confirm generalization. To evaluate performance, I used MSE, RMSE, MAE, and SSE. On the test set, the final model achieved an MSE of 21.54, RMSE of 4.64, and MAE of 3.69. The SSE value, around 32,000, is consistent with the dataset size and confirms that the model's total error remains very low relative to the overall scale of the. Both models performed similarly, but the baseline model was slightly more accurate across training and validation sets. This suggests that although AP contributed the least, retaining it still improved the model's overall accuracy. The baseline multiple linear regression model, with all 4 predictors, consistently outperformed the reduced model across training and validation. On the test set, the model achieved an RMSE of 4.64 and MAE of 3.69, meaning predictions were typically within about 1% of actual values. The scatter plot on the right here confirms this, showing predicted values closely aligned with actuals along the red diagonal. Overall, the model explains about 93% of the variation in power output, demonstrating strong accuracy and generalization. While the baseline model performed best, future work could explore more advanced regression methods or feature engineering to push accuracy even further. Thank you for your time today.